G'day guys, today we are looking at summing infinite geometric series, okay? Ones that don't terminate at a particular Tn, ones that go on forever. Now this relates right back to a gentleman from ancient Greece called Zeno, and Zeno was a gentleman about 500 BC who we would these days call a polymath. Poly means many. Math doesn't particularly mean maths, I don't think, in this situation. It means sort of studies, things that you are good at. So he was good at many things, okay? This was a sort of typical gentleman of the time, right up until a few hundred years ago in the Renaissance. You would have people before universities existed in the way that they do now, where you have an engineering building, a maths building, a philosophy building, and so on. It wasn't so artificially divided like that. Learning was a unified whole domain. And so there tended to be people who were good at a bit of everything. And typical cases would be people like Michelangelo and Leonardo da Vinci. I mean, da Vinci could build designs for flying machines. He could do mathematics. He could paint the Mona Lisa. He could do all sorts of things. All right, so what on earth does this have to do with geometric series, okay, and finding an answer to an infinite sum of a geometric series? Well, Zeno had a bunch of paradoxes that he had come up with, things that he knew were true but which he couldn't explain. This is what a paradox is. And he had many of these things, but one has become so popular that it has become known as the Zeno's paradox. And here's one way of explaining it. All right, Zeno's paradox. Consider we have a chicken that wants to cross a road that is 1 unit in length. Doesn't matter what that unit is, just one road width, okay? Now, there is a halfway point. In order to get across the road, the chicken must first get to that halfway point. So, the chicken walks half a unit. Now, there is half a road length remaining, and the chicken must walk 1/2 of that 1/2. I mean, if it's just walking from left to right, it's going to have to pass through that point at some point, right? So now it's a half of the total road length, which is 1 unit, plus a quarter. So a half plus a quarter. Now there's a quarter of the road remaining. At some point, the chicken is going to have to cross through half of the remaining half, which is a quarter of that remaining half. A half of that remaining quarter, which is 1/8 of the total road length. And the pattern continues, 1/116th, 1/32nd. Now Zeno didn't understand how it was possible to actually, for the chicken to actually cross the road. Because if you think about it, in order for the chicken to cross the road, it has to pass through infinitely many halfway points, all of which must add up together to give you an answer of 1, because we know that that is the width of the road, 1 meter or 1 unit or 1 whatever, okay? And Zeno thought, how can you do infinitely many of anything, add those terms together and get an exact answer? He thought that made no sense whatsoever. And it's a very, very clever intuition, but you can test it for yourself. If you try and walk across a class and touch the wall on the other side, you'll pass through a halfway point, and then when there's halfway remaining, you will walk through half of that, and then halve again, and halve again, and halve again, and it will not take you until the end of days to touch the wall. You will get to a point where you can simply reach out and touch the wall. So it is possible to have an infinite number of terms in a geometric series, and this is a geometric series because if we take, say, t2 divided by t1 or t3 divided by t2, we get 0.5, a half, okay? He figured out that it is actually possible to get an exact answer by adding together infinitely many numbers. But he thought, how can you add infinitely many numbers together and get an exact answer? It doesn't seem to make sense. So this is Zeno's paradox. And it wasn't made sense of until calculus came into existence thousands of years later under Isaac Newton and a guy called Leibniz, who were probably two of the most brilliant men who ever existed. I'm sure there were lots of brilliant women as well, but unfortunately back in the day, women didn't get the opportunities that they deserved in order to get out there and express their mathematical ideas. So who knows, we might have learned about this a little bit earlier from some very intelligent women if society had been a little bit different, but that's another story. All right, so how on earth does this relate to what we're studying at the moment? Well, let's dive straight into it. There are two types of sum, okay? So a bunch of terms in a sequence added together. And we're talking about infinite sums here, ones that go on forever. You have a convergent sum, which is a sum that gets closer and closer to a finite, specific, exact amount that is an infinity as that number of terms in the sum approaches infinity. Okay, so let's read that again. A convergent sum is a sum that gets closer and closer to a finite number as the number of terms in the sum approaches infinity. Well, the number of terms in our sum above approached infinity. There were going to be infinitely many sums. But the result of our sum, every time we added on a new term, got closer and closer to 1 because the guy was getting closer, the chicken was getting closer and closer to the wall, okay? And if you took that sum, if you wrote 1 million terms in that sum, added them together manually, you would get 0.999999999 and then a bunch of nines, but you would not exactly get 1, okay? That only happens at infinity, if you can even picture that. All right, so how do you calculate these things how do you calculate an infinite sum and its exact answer without having to sit there and do T1 plus T2 plus T3 and hit the plus button infinitely many times? Well, we have a formula, and it's a backdoor formula that enables you to avoid that process and still get the right answer. And here it is. So the sum of an infinite geometric sequence is given by T1 plus T2 plus T3 plus blah, 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 forever, where R is between -1 and 1. That's important for this formula to work. It doesn't work when you have a common ratio outside of that range. And so long as these conditions are met, then the infinite sum, which above, in the above problem, Zeno's paradox, equaled 1 road width, the infinite sum is simply equal to A divided by 1 minus R. So the first term divided by 1 minus the common ratio. It's that easy. Pretty unbelievable. And as we do, I'd like to prove that for you right now. You would think that such a complicated idea would have a really, really complicated proof, but it doesn't. It has a dead easy proof. And here it is. So we know that the sum to n terms equals A bracket 1 minus R to the n over 1 minus R. Now we only need to consider one thing to change that into the infinite sum formula. All right. Now, as n approaches, that arrow mean approaches, as n approaches infinity, We can't say n equals infinity technically because infinity isn't a number. So we sort of cheat. We say as n approaches infinity with an arrow, r to the power of n approaches 0. All right, now that's confused you all, so let me try and explain. Let's pick a random r value, all right? And I've chosen a half because in the Zeno's paradox problem with the chicken, r was equal to a half. A quarter minus a half, an eighth minus a quarter, and so on. Now we're considering what happens to the sequences, to the terms in the series as the power, the n value, increases. Well, r to the n here is a half squared, which is a half times half. Half of a half is 0.5. What about a half cubed? Well, that's a half times a half, which is 0.5, times another half, which is 0.125. All right, a half to the power of 4, that's a half times a half, all right, times another half, which is a half squared times a half squared, all right, which is a half times a half times a half times a half, which equals 0.0625. Now you can see these numbers are getting smaller and smaller and smaller. Now if I were to take, I don't know, a half to the power of 60, the really large n value, just putting that into my calculator, see what I will get. I get something with 19 zeros after the decimal place and then an 867. So 0.00000 blah 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 blah, 19 zeros and then 867. Almost 0 but not quite 0. Okay? You would have to go all the way to infinitely many terms to get exactly 0. Alright, so what about negative r values that are between -1 and +1? Well, I'm going to choose negative a half this time. So negative a half to the power of 2 equals a half. Negative a half to the power of 3 equals minus 0.125. Minus a half to the power of 4 equals positive 0.0625. Okay. And although those numbers are oscillating on either side of the plus and minus sign, they're still getting closer and closer to 0, aren't they? All right. So what does that tell us about our proof? Well, once again, as n approaches infinity, as n gets larger and larger, r, so long as it's between -1 and 1, to the power of n approaches 0. Gets closer and closer to 0. All right, now that means as n approaches infinity, 1 minus r to the n, which is this term here, approaches 1. Because if r to the n ends up getting to 0 at infinity, when n equals infinity, then we'll be left with 1 minus 0, which equals 1. And if you substitute in here for 1, you get a times 1, which is a. Now what about the bottom? 1 minus r right here. Okay. Well, that doesn't change at all, does it? There's no n's in there whatsoever. So that just remains put in the final formula. And the proof is done. The sum to infinity, the infinite sum of a geometric series, is simply equal to the first term divided by the difference between 1 and the common ratio, which is pretty amazing. So if we were to apply this formula to the chicken problem, we should get that the infinite sum equals 1, because we know that the sum of all of those halfway marks should equal 1 unit, because the road we measured as 1 unit in length. Okay, so let's test it. So here's our sequence that goes forever: a half plus a quarter. I keep saying sequence when I mean series, sorry. A half plus a quarter plus a 16th plus a 32nd plus ... forever. First term equals a half. R is T2 divided by T1, or you could do T3 divided by T2 or whatever. No matter what, you're going to get a half. So now we have, change colour because this is getting messy. A equals a half, R equals 0.5, and we substitute them into our formula. R, the infinite sum, I forgot my infinity sign, and I've even called it an R because I'm an absolute donkey. S infinity equals A over 1 minus R. We're expecting this to equal 1. Well, A equals a half over 1 minus R. Well, R is also a half, so 1 minus a half, which equals a half over a half, which equals 1, as expected. So the formula works, okay? And that is how you find the infinite sum of a geometric series. We didn't do any examples, guys, but this formula is really, really easy to use. And I believe next week, the school's now saying we're going to have one time per week where we meet up and discuss some questions and so on live. So this might be something we can talk about. But please hit me up with questions when you're doing the exercise if you have any trouble, and I'll see you next time.